Hello and welcome to another episode of Ether Cosmology. We're on episode 12 or 13, I can't remember. But anyway, welcome to the new episode. If you want to before we begin, if you want to support the channel, I have a coffee account. You can send one-time donations or you can sign up for a membership. So it's kind of like Patreon but without having to use Patreon, so you can check that out there and if you want to. So we'll get into the Ether Cosmology now.
Things that we can quantify and measure here on Earth in our own frame, our own reference frame, aka what I would call measurable reality. So yeah, I guess Alan, maybe I should repeat what I just said for your audience.
Oh yeah, dude, that'd be great, dude. My bad. Sorry, I took an extra second there.
So we're gonna do GPS first, correct?
Yeah, we'll get into the speed of light and how they've come up with a way to synchronize time with it, and that, and then we'll get into the history of the constancy of sp or the constancy of c, alleged
Perfect.
constancy. All right, cool. So let me pull up my thing, share screen. All right, should be good. Everyone in? No. Give it a second, or it's just you. I got
everyone that matters.
All right, let's see here. The boys will tune in when they're ready. All right. Anyway, so here's a picture. Here's a picture of an old atomic clock model taken from this YouTube video here. If you want to check out the link, it'll be putting it in the YouTube description thing or whatever. You can check it out there. It's a really cool video. So they have their old atomic clock. They put it, or here's what the clock looks like taken apart with the shell off. We'll get into the specifics of how it works and what they say they're doing. And as we go over how they say the atomic clock works, I'll kind of cover how I think it works. Slightly different interpretation, right? So we'll get into that. So we look at before we begin, we'll look at the periodic table. We'll look at the valence electrons. So at the top of the periodic table, you'll see some numbers here: 1, 2, 3, 4, all the way up to 18. These are the valence electrons, and they're in the interpretation of how they explain what's happening inside of an atomic clock. That'll be important. And then right here they use, this is the cesium. So they're 55 electrons. So this is what they're using for this. So the important thing to note is that it has one valence electron, right? All right. So in their model, what it would look like, hypothetically, the distribution in the Bohr model, you would have your nucleus, you would have your 2 electrons here, and then you would have your 8 distribution rings. I don't know the rules for each ring for the distribution, but the first 3, the third one holds 8 or something like that, and then whatever. So it ends up breaking down where cesium only has one electron on this outer ring here, right? So that's what the valence electron is. This outer ring, how many electrons are on the outside here? And the way that they talk about the atomic clock and their interpretation of it is they're focusing on just this. They say that they're just focusing on this particular electron, right? Okay. In the model of the cesium, right? Okay, so this is a diagram of what's going on inside of here and how all this works, right? So what they have here is they have cesium in a little tube. They have it in what they call a cesium oven. When they heat that up, it produces gas. Cesium has a very low melting point, so it doesn't take very much to get it going. I think if you just expose it to air, like immediately, it's one of those deals where it just immediately starts combusting and stuff. So they got their cesium oven. They got cesium gas. They use what do you call it? Like funnels and little holes and stuff and slits to funnel it into a beam, like to collimate it, and then it comes out as a coherent beam where the gas passes through a magnetic field. Here, any energy that's too excited or whatever will be bumped out by the magnetic field. The rest of it will pass through here into the radio wave cavity. And here it will be the resonant. I'm sorry. In here, the cesium vapor will be blasted with radio waves until the radio waves reach the same resonant frequency of the cesium. Because apparently the big deal with this is that it oscillates at 9,100,092,000 or 192 million oscillations a second, right? So very precise and well-known oscillation rate. So they're calibrating the radio waves to match that frequency, and when they've done that, that leaves the cavity. The excited vapor in cesium leaves the cavity out of another magnetic field, where any energy that's outside of the parameters of that 9.192 gigahertz frequency is exported, or just kicked away, and then it's everything that's the proper frequency hits this ionizer. So the ionizing the gas at that frequency with the radio waves, that energy produced from that gets converted into electricity. So when it hits the electron multiplier, what's going on here is it's just electricity is being bounced back and forth between these mirrors, amplifying the signal, and that signal is interpreted as that's what splits 1 second into 9,192,000,000 oscillations per second. So that's how you can break down a second into a billionth of a second. That's what they're doing. So once they get that frequency, once it matches that oscillation rate of the cesium, they lock in their radio waves so that they're at the exact frequency to match the cesium, and they use this in a continual loop to keep time down to the billionth of a second. And okay, so the thing to note with this is, now that they've got this precise device that keeps time, how do you synchronize more devices to it, right? How do you come up with a network, a way to synchronize all these clocks? So introducing the Einsteinian clock synchronization method. This assumes that the speed of light is c, and they use what's called a half speed. So like the one-way speed, they're assuming that the travel speed going to one way is also c, right? So the way that Einstein explains clock synchronization, I'll just read through this wheel here. Then we'll touch on the diagram and explain what everything means. So the little a and the little b is alpha and beta. These are two atomic clocks, and the capital A and capital B are alpha or A and B. Okay. So we assume that the speed of light is constant in both one-way and two-way trips. Okay. So first part of the synchronization, assume the speed of c in both directions. When moving clock A intersects with stationary clock, when moving clock alpha intersects with stationary clock A, a signal is sent to beta, encoding alpha's starting time. When moving clock beta receives the signal, it applies a half-time correction to account for the travel time of the signal as it's sent from A to B, right, or alpha to beta. The moving clock beta and the stationary clock B will then synchronize their times with A, using a corrected signal based on their times based on that 1/2 travel time, right? And any difference between the moving clocks alpha and beta is adjusted to match the stationary clock A, and as well as moving clock alpha, right? So to keep everything in sync, basically they're assuming C and using half-time corrections to correct for the travel time in between to keep everything synchronized as they intersect, right? So in theory, if you have a stationary clock here and moving clock here, a system of moving clocks here, and they're yeah, all right, and they're and the moving clocks are in motion, right? So when they intersect, when alpha and A intersect, a signal is sent to beta, and it says, "Hey, I'm sending the times at this timestamp. I'm sending a signal." And beta goes, "Cool, okay, no problem. Let me subtract the half of the speed here for the flight time, and then my clock will be corrected," right? And then they compare and contrast to make sure they're all good. And if the speed of light maintains constancy, then these clocks should be in sync forever, right? Essentially, that's the idea. So what they've found, though, is that the atomic clocks require corrections. So there's a retardation to the clock that's proportional to the velocity of the craft, whatever is carrying this device, right? What that means is, if you think about that 9,192,000,000 oscillation rate, it's basically oscillating one less time, per whatever the velocity is, right? So if it's, let's say like just for example, right, to make it simple to conceptualize it, let's say there's a craft traveling at 1,500 miles an hour. So it would be like 9,192,000,000 minus 1,500. Like it's just oscillating that much less, right? So to compensate for that, they actually have to add in energy on their microwave inputs to make sure that it matches that resonant frequency of the cesium, because the electromagnetic waves are retarding. So to keep it in a line, they have to these atomic clocks are Sagnac corrected. They're accounting for the Sagnac effect. Now we're told that these clocks are accounting for the rotation of the Earth underneath them for some reason, and but also in addition to that, from this equation, right? These equations are taken from the what do they call it? The International Radio Consultative Committee, International Telecommunications Union, right? So the CCIR, so like the people that set the industry standards for how these things work and all this, right? So in their equation, they're saying Earth rotation velocity and also the velocity of the craft. Okay, so the velocity of and this is equivalent to correcting for the Sagnac effect, which is basically saying the speed of light is changing proportional to the velocity of the observer. So this isn't supposed to be happening. This is why Einstein clock synchronization doesn't work. So they've done experiments in the 70s to to figure out how to get atomic clocks to work and what synchronization methods they should use and whatnot, right? So the homies Hafele-Keating in 1971 did their around the world clock west and east trips, carrying 4 atomic clocks that became so wildly out of sync and so not within the predicted parameters that the experiment was basically a wash. A quote from their 1971 unpublished paper that was what's it called, like FOIA requested from the military, because the military funded this whole experiment. So this was FOIA requested from their like debriefing or whatever after the experiment. So this is transcripts from the conversations that they were having with the people in the room, that funded everything and all that, and some other scientists. And they say, this is a quote from Heffel. He says, the results of the analysts are in a reasonable agreement with theoretic predictions. However, those who doubt the validity of the conventional relativity theory, and there are many who are in that category, probably will not be converted by the results shown here in Figure 4. Indeed, the difference between theory and measurement is disturbing, and the final analysis does not improve agreement. And the improved version of an improved version of the experiment should be given serious consideration. So in the works before they published their 1972 paper, they were like, yeah, it's pretty lackluster. Like the clocks wildly went out of sync. So when they're all going east, they're all supposed to lose time. When they're going west, that they're supposed to gain time. And it only happened for 2 of the clocks in each section, and then it did it in the opposite direction on the other, going the other side. And then there was spike variations that were outside of the parameters of their error margins, but where they just kind of reset the clocks. And that actually, nobody really knows why that happens or how to explain that. It's the creator of the atomic clock, Louis Essen himself, said that's just something that happens. So this device, actually, the only thing that's really constant in here is the cesium, right? Its natural decay rate isn't retarded by the motion. The way they're fixing the calibration and the precision comes from the adjustments made to the electromagnetic signals that are being that are supposed to maintain a specific resonant frequency. So that's why all this is happening, right? And as these clocks are in motion, going with or against the rotation of the ether field, they experience retardation that goes with that, right? And to fix this, right, Einstein synchronization didn't work. They had to add the velocity of the craft because there's a first order dependence on the retardation. It's not a random thing. It's not statistical anomaly going through, different gravitational potentials. It's a first order dependence that, if not accounted for, this clock would not work. All right. So that is the constancy of the speed of light. So they're basically giving it a little booster pack, right, to account for that. So that's That's Einstein clock synchronization and GPS. So later in 1972, Hafele-Keating republished their work where they brought their observations in line in alignment with the relativistic predictions, and now they tell everyone, congratulations, we proved time dilation and all that stuff. So, and keep in mind, this Sagnet correction being applied to the craft is a direct refutation to relativity theory. The craft should have no way to know its velocity or have to be corrected for it. And the fact that it has to be corrected on the first order kind of tells you exactly what the mechanism for that is, and that would be an ether. All right. So that's atomic clocks and GPS for now.
So
So
yeah, two points on that.
Mhm.
First of all, what I found was interesting when me and you were talking about it earlier, when we really got into how an atomic clock works here. Um, it's kind of hard to conceptualize, like, why would specifically the atomic clock have the exact same proportional relationship to east to west movement and west to east movement as like a radio wave does in the range measurement equations for GPS. But once you realize that you've got this whole thing is like an electromagnetic process with the radio waves and the magnets, um, that makes sense that you would have a proportional decay rate that's proportionate to the exact same motion through the ether, essentially. So yeah, that was really interesting. And then also on the Einstein clock synchronization, I recall, is he referencing Hafele-Keating? I know in the Marmot paper he kind of indicates that the Einstein clock synchronization, not only does it not work, but it doesn't work to an order of exactly what you expect it to not work, with not taking into regards the relation or the relative velocities of the clocks.
I don't recall if he did that. Let's see. This was in 1990, so yeah, he would have known about it. Let me see. I don't see it cited here.
Because maybe I don't really know what his source was exactly, but I do believe that he indicates that. Let me pull my notes up actually.
Yeah, what you're
But
saying sounds familiar.
like that exact, like when you do the Einstein clock synchronization, the exact amount it's off by is like, oh, because it's exactly because you didn't account for the proportional velocities. Um,
Are they doing this math like backwards so that they can keep C constant or appear to be constant?
well,
What's that?
they account for the velocity in the Sagnac corrections. So
Yeah,
like they are.
they're
Go
yeah
ahead.
they're ratioing their velocity against the speed of light and correcting by that amount.
Wild. Yeah, I see it right there. C minus V. Yeah.
Divided by, or I don't know where you're reading. Never mind. Yeah, but yeah, that's their ratio.
Equation 16.
They're just subtracting
Well,
it and then correcting for that amount. So what Marmot ends up pointing out here is that these corrections that we're told are due to um, XYZ relativistic effects are actually just equivalent to accounting for the relative velocity of the craft, aka they're identical to the Sagnac effect. So it's one of those cool things where you can like solve a math riddle or whatever with a different way to propose it, you know? So it's just like dressed up, but it's literally the Sagnac effect.
is that figure 3 an AE map?
Figure 3, yeah, probably. But yeah.
So I guess he kind of infers it indirectly, because he says that
Oh,
Einstein's says the original Einstein's clock synchronization method was perceived as an attempt to set up an identical display. This is on page 1274. Right under right under equation 13. Here we go. So yeah, equation 13 shows a display. However, unexpectedly, where's that at? Here we go. However, unexpectedly, in a moving frame, this synchronization method does not give that expected result as obtained in the station frame. Equation 13 that shows that the display on clock beta gives an apparent time, which is earlier than the display on clock alpha. This is a fact coming out inevitably from the principle of mass energy conservation and Einstein's synchronization method. This deficient synchronization of clock beta is responsible for the Sagnac effect that will be explained below. So he's kind of like leading into it essentially and inferring that it's exactly because of that.
Yep.
Yeah, and he also says here, it's funny, he says, the difference in clock synchronization is normally undetectable and even appears quite normal for an observer traveling inside the moving train. Basically just saying it's undetectable well, if you're with the clock, you're not going to notice it. But yeah, in any case, pretty interesting stuff.
Yep.
So yeah, I guess now we can go from there back in time.
You wanna
I can go ahead and share my screen or share my presentation. Let's go to the top here. And let's see.
Nice. I like that aesthetic, man.
Grab myself a couple of new LibreOffice themes.
That's dope.
So yeah, today we're going to talk about, we just talked about this whole thing about the relational velocity of C. And so now we're going to go back in time. We're going to talk about the history of this idea of C and this measurement of C, or what they call the speed of light. We're going to talk about, measuring the induction rate of light. And there have been measurements that have been made out of the lab frame. So basically stepping out of measurable reality and making assumptions, and in the lab frame, which means that it was measured essentially on the Earth in the same time that we exist in, not in a hypothetical space-time. So yeah, real quick here, we're going to go through Galileo Galilei, 1838. That was in the lab frame. Romer was out of the lab frame. Fresnel had a lot of ideas about light. Arago, 1838, in the lab frame. Fizeau, 49, in the lab frame. Maxwell, 65, derived from constants that were taken, or variables that were taken in the lab frame. Michelson-Morley, 1887. We'll get into that. Although I think we're all pretty familiar at this point. Albert Einstein, out of the lab frame, was what he proposed essentially is, how about we just take a step out into a whole new idea outside of the lab frame. And then Dayton Miller came along and made a bunch of measurements in the lab frame.
Hey,
so,
before we continue, what is the lab frame and what does it mean to be in and out of?
Well, so you can that's a pretty loaded question, kind of. Well, it's basically this idea of kinematics and dynamics. When you're inside of the lab frame, you are using measured variables. You're using measured reality to make predictions about reality, and the rules of physics apply to everything that you measure, because you are measuring them from within reality.
So
out of the lab frame, maybe it's easier to explain out of the lab frame, which means that we'll get into it, because we're going to get into Romer in just a second here, and I think that'll be a good distinction right there.
Okay.
Unless you have any other thoughts.
No, I was just gonna say, like, that's great. So, like, in the lab frame would be where you can manipulate the variables and have controls, IVs and DVs and things like that. The out of the lab frame would be like abstractness through mathematics. Things that you can't control or really discern. It would be like more of just observing something and having like making observations and coming up with constants and things like that to describe the interaction, where you can't really interact with what you're describing mathematically, right? So
and actually there's an important distinction that we'll get into I guess we'll probably wait till when we get to Einstein, because at least with Romer, he's using kinematics of the cosmos, so there's actually some predictability going on there because the cosmos have some predictability. And then whereas once we get to Einstein, we kind of throw predictability out the window, and everything is just purely ad hoc, or post-dictions. But in any case, so 1638. Galileo Galilei is like, hey, how fast is light, quote unquote. So he came up with this brilliant idea of, person A is gonna stand over here on this hill, and then 1.5 kilometers away, person B is gonna be here, and they both got lanterns with blankets over them. And then he's like, person A pulls their blanket off the lantern, and then when person B sees it, they pull their blanket off the lantern, and then person A is like, oh, okay, I can see the difference in the time there. But I think we all kind of can tell on its face this is not a super great way to measure the quote unquote speed of light. So yeah, he just decided at that point, it's either instant or it's too fast to measure. He was at least humble enough to say that he maybe just couldn't measure it. And then in 1676, as the lore goes, Romer comes along and he observed the eclipses of Io, one of Jupiter's moons. And he was watching the eclipses and noticed variations in the eclipses. And he presumed the differences were due to the time it took for the light to travel different distances to the Earth. And then based upon those different distances, that the eclipses would have been. I think he observed a total of, I want to say, 30 eclipses. As so the lore goes, he deduced a potential finite rate of 220,000 kilometers per second for the quote unquote speed of light. And notably, that is 26% lower than the currently accepted value of around 300,000 kilometers per second. So interesting there. Now, that's all based on presumed distances. It's kind of how that whole model works is within this framework here.
Scaled invariantly to that.
Yes, sir. So that was 1676. Now we've got 1818, Augustin Jean Fresnel, and he published Memoir sur la diffraction de la lumière, Memoir of the Diffraction of Light. He supported a wave theory of light, and he developed equations regarding light behavior in various media, and he hypothesized the idea that light is dragged by a moving medium. And actually, not only did he hypothesize that idea, but he actually came up with this equation too, which is Fresnel drag. And we're going to get into this in a bit, but just wanted to go ahead and shout out right now that somehow he had derived that equation, even though it was just a hypothesis. But I don't have a ton of information on Fresnel, unfortunately, today, other than to say that he was certainly a G. So then 1838, Francois Arago comes along. He discovered this idea of the Arago spot. And what that is basically you take a beam of light and then you put a sphere in the middle of that beam of light, directly in the middle of it. And then what you get, the diffraction rate or the wave pattern of the light on a wall looks like this. You get these ripples around the outside, and then you get this dot in the middle. And that's because of the intersection of the way that the light is traveling around the dot. Essentially, you have an intersection of like a equidistant electromagnetic waves coming in from that to that center point. And basically, so this helped him to predict. Yeah, that's why he was a proponent of wave theory, and he predicted that the induction rate of light should decrease in denser medium. And this is the basis of Airy's failure. And if we, I don't actually have a slide about Airy's failure in here, but the idea with Airy's failure was that they were going to use this difference in the denser medium to do a measurement, looking through a telescope without water in it, and then a telescope with water in it. And then if you needed to tilt the telescope with water in it forward, then it meant that the proportional rate of the velocity, essentially that the stars would have had to been moving, not you. You're looking at the difference in that light travel and that through the telescope there. But in any case, they called it Airy's failure because, go ahead.
I got a slide for you. Sure. As soon as Discord stops, there we go. You want to pull that up real quick so you can show people the telescope angle?
Oh yeah. So if you're in listening, watching in Discord, you're just gonna have to go look in chat real quick. But yeah, here's just a quick demonstration of Airy's failure. Telescope stationary, so if the light was coming straight down, you would keep it stationary and straight up. If you have, but we actually have to tilt it. And if you have to tilt it without, or when you put water in it, basically it shows how that ratio would change. Yeah. But that premise for this experiment comes from essentially what Fresnel had hypothesized back in 1818. So yeah, Arago also did a determination of C in the lab frame, but I don't have that with me at the moment. Let me see. Oh, also notably, he did work with polarity, which is just further evidence of light being a wave, not a particle. But we'll move on here. So in 1849, we have Fizeau comes along, and he did determinations of C in the lab frame as well. So on Earth in reality, not using the stars and assumptions from the stars. And he was the first one that we have documented Fresnel drag tests that were performed with. And so he says here, the success of the experiment seems to me to render the adoption of Fresnel's hypothesis necessary, or at least the law which he found for the expression of the alteration of the velocity of light by the effect of motion on a body. And so yeah, that was him talking about the Fresnel drag test, and we'll get to that in just a second. But real quick, so this is a description from Fizeau's book. And this is a paper he wrote. It's on the hypothesis relating to the luminous ether and an experiment which appears to demonstrate that the motion of bodies alters the velocity with which light propagates itself in their interior. So basically, light propagates through something, and there's a proportional velocity of that. And he actually did. He says here we're indebted to Arago. Experiments of Arago and Fresnel. The difference of refractions of dry and moist air have proved the extraordinary sensibility of the means of observation. I'm not going to read exactly how he did this here. It's quite a mouthful, especially without a diagram. It's really hard to visualize it. So yeah, here though is now he did perform the Fresnel drag test, and or actually. Go back here. So this was the other way he did it in the lab frame. And this is basically he has a light that he shined and through this mirror here, and then he had a wheel turning with teeth cogs. And as the light goes through those teeth cogs, it came through and hit a mirror that was really far away. And then that light would reflect off the mirror and come back through the teeth cogs, and then hit this mirror here and then go to the observer. And so the observer was then able to look at the pulse rate of that light coming back from the mirror, and they were able to deduce one of the first measurements of C from here on Earth in the lab frame by using this setup here. But now back to the Fresnel drag test. This is really, I think, really important to understand. So the layout here in this first original Fresnel drag setup is you have sunlight coming in, and you have a mirror here that splits the light. You've got one wave that comes through this way, and one wave that deflects down to the down south here. So one's going east, one's going south, and then this mirror deflects it through here, and it goes through this mirror to the eye of the observer, or you would create a fringe pattern, and then here it's bouncing off this mirror. So you've got two different light waves, or one light wave that gets split into two, and this wave is going against the moving flowing water. And this wave is going with the moving flowing water. And so when these come back together, you get the displacement in the fringe pattern there that you can use to then calculate the proportional velocity of that light against the flow and with the flow of the water. And what they found is exactly what Fresnel had hypothesized with his equation, which is that there's a 44% proportional velocity that comes with that light to the observer there, because there is a refraction rate as well, but the velocity of this water going through this pipe here is that velocity is carried over proportionally 44% against this wave and with this wave. So clearly there is a drag effect happening with that wave itself. The light is propagating through that medium, which would go with our ether theory, which is the idea that light propagates through a medium and is relative to the proportional velocity of that medium. So yeah, moving on. 1865, J.C. Maxwell, we all know Maxwell's equations. He used known values of the electric constant and the magnetic constant in his electromagnetic wave equations. And basically the idea came about that light is an electromagnetic wave. And then in, what year was it? 1887, right? Michelson-Morley experiment. I don't know why I didn't put the year on here. They came up with the idea of the Michelson-Morley experiment, which used light interferometry, kind of similar to this setup, but just take the water out. And basically, they didn't need the dependent variable here was what their calculated speed of C was, or the speed of light, which was well known at this point, thanks to Maxwell. Were fairly well established. So that was the dependent variable. And then the independent variable would have been the orthogonal vector direction of the interferometer itself. So as you would turn this device in a circle, you would get a different displacement in that fringe shift that would be proportional to the absolute motion of the Earth itself. You don't have water flowing in the Michelson-Morley experiment because instead you're trying to measure the absolute velocity of the Earth itself. So you would have the Michelson-Morley experiment was a much more sensitive interferometer, and it was the first of its kind. But they knew exactly what they were doing, and that's the whole point of this whole presentation, is that, you look through this timeline up to here, they had done lots of measuring. They, at this point, especially between Fresnel, Arago, Fizeau, Maxwell, they knew very well at that point how the proportional relationship of the velocity of light worked. And so that's the whole premise of the Michelson-Morley experiment. And one thing that's really interesting that was pointed out to me recently is that you can't actually find the proposals for the Michelson-Morley experiment. You can find the actual paper itself for when they first did the experiment, but you don't see a lot about how they knew exactly what they were doing, because they don't want to talk about how they knew exactly what they were doing, because the result was not equal to what they expected with the Copernican principle. They expected a speed of 30 kilometers a second. Instead, they got around 7 kilometers per second. And that result can really I would say only be explained. Well, you could make up some kind of theory with some kind of slow-moving Earth maybe, but it's nothing close to the Copernican principle. And it actually is much better explained, in my opinion, with a stationary Earth in an ether wind, which up to that point, I guess I don't know if there had been much talk about an ether wind up until that point. But so in 1905, Albert Einstein came along with special relativity, and I don't have a lot for this slide, as you can see at this point. But the idea here was that, when you say that, I mean, this literally was kind of the whole premise here, because they said that the entire apparatus contracted in direct relationship to the sun. And in that case, they had to call the little bit of fringe shift that they did measure, they had to call that instrumental error, although they then came along later on with Michelson-Gill-Pearson and measured the exact same thing with a higher degree of precision and called that Earth rotation. But I digress. The point here is that special relativity, this is like they try to say that Michelson-Morley was proof of the non-existence of an ether and proof that we are in motion or something. And it's actually, this is purely outside of the lab frame thinking. You cannot verify this unless you can somehow step outside of reality and verify it from outside of reality, in which case, what are we even doing? So this is outside of the lab frame. Let's come back to reality. Let's step back into the lab frame, and let's talk about Dayton Miller in the 1910s, 1920s. He looked at what was actually measured with the Michelson-Morley experiment, the tiny amount of fringe shift that they did get, that 7-ish kilometers per second that they measured, and he started to measure it more precisely over the years. And he through 1921 through 1926. His Mount Wilson experiments, he used specifically this idea of C, this known propagation rate, of the induction rate of electromagnetic waves to measure ether wind, and he found that the correlation of those measurements was in line with the altitude and the equinoxes. So if you're getting more sensitive and higher velocity readings at higher altitude, then clearly that cannot be this relative rotational motion of the Earth, because you wouldn't get an increase with altitude. And the equinoxes should be utterly irrelevant if it's the rotation rate of the Earth, because the equinoxes, that means that it's correlating with the orbital motion of the Earth. And the orbital motion is not what they measured. They claim they measured rotation. So you can't say it has anything to do with the equinoxes. And that's why they had to bury Miller. And that's why, when Galev came along in, when was it, 2001, and essentially corroborated a lot of Miller's work and did further testing on the interference of dielectric materials on these interferometers. Galev showed that specifically the dielectric protection that they were using at altitude in all these different experiments was essentially blocking out the measurable ether wind, and that's essentially what Dayton Miller had hinted at as well. But yeah, and with LIGO, the LIGO facilities, those are underground, let alone protected by dielectric materials. Although they do still get measurements there, but that's all run through a convolutional neural network, and it's based on, they have models baked into that whole system. So not only am I skeptical of everything that comes out of LIGO, but I actually happen to, you can look at what's been shown in their regressive models in throughout time, that they actually have to account specifically for variations throughout the year and variations throughout the day, which also interestingly lines up with what Elias found with his pendulum, and variations throughout the year and variations throughout the day, and was corroborated by Saxel at Harvard in 1970, and they measured the same thing with their pendulum for 17 years. But anyways, that's kind of the end of that. Me and Alan have been looking a lot into the history of these measurements of C. It's pretty interesting to dig into. It's kind of all set up for, what they were thinking. Freynell, thank you. What they were thinking when they went to go do the Michelson-Morley experiment. But yeah, that's pretty much everything I have for that presentation. Alan, should we talk real quick about our Pound-Rebka light bulb moment?
Yes. Screen sharing now.
I guess maybe before that, real quick, does anyone have any questions or like anything they want to say about the GPS stuff or about the history of C stuff?
Yeah, other than the shielding, were there any other specific experiments you can reference right now that Galileo did as far as properties of light?
Oh yeah, yeah. His altitude tests. He used one-way propagation of radio waves with he used atomic clocks, right, Alan?
Who's that?
Galev in 2003. His radio wave from altitude.
Not sure if he used atomic clocks.
Well, in any case, he used radio waves from altitude and then propagated down to two different altitudes at two different relative positions, and did the math from that to basically deduce that there was a relative velocity difference to different or from different altitudes. So essentially, the higher up that you are, there is a greater rate of ether wind velocity, or what, it causes a different proportional rate in the velocity of light. But yeah, so that was another experiment that he did, another whole paper, also insanely relevant to this. That was also shown by, didn't Monero show that as well, Alan?
Yep. He showed
that.
He showed that there was a fluctuation that corresponded to the equinoxes, similar with Miller. And they left their device running 365 days for 3 years straight.
But specifically, they did not. Did they do altitude or no?
No, not that I'm aware of. They just left it in the school.
Isn't there one other altitude measurement I'm not thinking of? I think
so dude, they did balloon test. Let's see here. Where was the balloon?
But didn't they measure like literally no fringe shift with those, or it was like completely arbitrary directionality?
No. The first one, they measured a fringe shift that matched Miller's, and then the second one they sent up, they said, no, we didn't get nothing. And then Kennedy and Thorndike did their thing, and they measured of using an apparatus that wasn't um, the arm lengths weren't proportional, like in the correct way, like how they were supposed to be, and that measured 26 kilometers a second. And then
Oh,
they straight up say, oh no, that measured nothing. Like they throw that one out and call it a confirmation that the speed of light doesn't change, and it measured a fringe that with their device that would correspond to a velocity of 26 kilometers a second. So they got close to that elusive 30 kilometers, but they can't have it. Like they already backed away from it, and then they would have to like further substantiate it, and then it would turn out that it's due to the arm lengths not being proportional, all that. But yeah,
even rigging it's really hard, huh?
yeah, yep.
So yeah, me and Alan were talking earlier, and Pound-Rebka
Oh,
came up.
mm,
Are you okay? I thought you were pulling it up. Okay, cool.
yep, yep. So Pound-Rebka here, they did an experiment in 1960, and whoops, where's my? There we go. Sorry, they did an experiment in 1960 and 1965 using radiation, and they were basically the way that they did their experiment. They had a radiation source at the top of this tower here, 75 feet, and then at the bottom they had a detector, and then they did the experiment in this configuration, and then on the inverse, so source at the bottom, detector at the top. And what they found when the first experiment was inconclusive, so and their published paper was titled what is it? I just added it here. 1 second. Their paper was titled "The Apparent Weight of Photons" in 1960. So inconclusive result. And what they were getting at was they couldn't tell the difference between a photon, quote unquote, gaining acceleration, meaning c plus v, like, or I'm sorry, c minus v, like it went faster, going down, um, and on the inverse going up, it was as if it had to overcome the same gravitational potential, so like the same exact 9.8 meters per second, that they say things fall at. They say that the electromagnetic propagation was acted on such that there was a frequency shift proportional to that amount of acceleration gained. Now, the reason that they like confirm this is because the detector that they were using in this experiment is only accepts a certain frequency shift of the wave, right? So it has to have a specific Doppler frequency shift to it for it to be for it to even register. And otherwise, it's not. The detector is going to be like, "Nah, I can't hear you, bro. Like you said, you're a photon. Like I don't know what that is." So unless it has that proportional velocity, right, or frequency shift, right? So the issue here became they were like, okay, we don't know what to make of this. So they did another rendition in 1965 where they used gamma radiation. The purpose here is that gamma radiation is supposed to be neutrally charged, meaning it doesn't react to magnetic waves or electric frequencies. So they were really trying to isolate out the variables of the experiment to say, like, okay, because there's an effect called the Stark and Zeeman effect. So when electromagnetic radiation passes through an electric field or a magnetic field, it changes the frequency of the light, right? Essentially, right? And it can have varying effects on it, and basically um, it can interfere with spectral or spectrograph readings and such, and all that stuff. But anyway, it's a known effect that'll happen, right? So they went back at it with neutrally charged energy, and they were like, okay, we'll see what happens here. And the detectors again detected a frequency shift in the radiation. So so they published their results, and we're going to read we're going to read like the conclusion basically from their experiment here. So it is not our purpose here to enter the many-sided discussion of the relationship between the effect under study and general relativity or energy conservation. It should be noted that no strictly relativistic concepts are involved, and the description of the effect as an apparent weight of a photon is suggestive. The velocity difference predicted is identical to that of a material object would acquire in free fall for a time equal to the flight. So that's 75 meters top and bottom. They're saying, you know, the that there was a frequency shift there, and they don't know if if the causal mechanism of that was the light was traveling faster, or if it had to overcome gravitational potentials, right, from the Einstein theory. So basically, that's what they were at with that. They made the theories were the same. The relativistic prediction and the classical prediction made the same prediction in this experiment, right? Um, and the reason, so it gets crazy too because they say in the relativistic paradigm, the speed of light is the same, right? So they'll keep the same speed, but they're okay with a Doppler frequency shift proportional to a speed outside of the speed that the wave's traveling, right? But they say that it just like hard encodes to the frequency of the wave spectrum there upon analyzing it. So they didn't know really what to do here. So at the end here, they close out and say, the view of the local time scale depends on the gravitational potential appears to be a coherent source for confirmation. The present experiment is unable to distinguish between frequency change and velocity changes. No, so the frequency change would be the speed of light is the same as it falls down, but the frequency changes proportional to the velocity to close this distance, right? And they say that but the speed stays the same, right? Like c remains constant in that interaction, just the frequency of the light change or of the energy changes, right? And for the classic theory, the velocity changes. They're saying that the frequency and the propagation rate change, right? Because obviously they're proportional. You wouldn't like it's so crazy that they think that it changes without being proportional to the velocity of the wave. But anyway,
The frequency shift is a bit confusing to even like try and get into because it really is it's really ad hoc. It's really nonsensical. I mean, they're
I
just
have a
like,
question about that, Toby.
yeah, go ahead.
So this is my thought. I think it makes perfect sense why they said that because velocity is distance over time. So if you presume the time to be a constant and the distance to be a constant, that means the velocity has to remain the same. Therefore, if it's actually changing velocity, what it's going to appear to look like is that a different number of cycles per second is hitting the target within that same elapsed amount of time. Does that make sense?
yeah,
Yep.
Yeah, so that's probably why they say it's a frequency shift because it's actually just a velocity shift, but they're forcing time and velocity to be the same.
yeah. That gets into invoking absolute space to preserve it for certain to explain certain experiments and stuff, right? But to maintain that constant velocity, they would that's where they can't explain actual fringes and stuff. But yeah,
But it says in the last point in green, the present experiment's unable to distinguish between frequency change and velocity changes, for example.
no, absolutely. And then it further says it appears that if the experiment comparison of clocks, so basically they want to introduce atomic clocks to this, so they can time it to see if C goes faster, right? And sadly, they never followed up on that. That was the end
Yeah,
of
so like
that was the end of the experimentation line for them, dude.
so it's really crazy because you think about how like their whole model is built around C being constant. So all those distances, when they talk about the light that we get from the sun being 8.5 minutes late and all this stuff, or even earlier when we were talking about Romer and how he's presupposed a bunch of distances to calculate a random shot in the dark at the velocity of light. Um, like that's all based around like, or at least in the current model, that's all based around this constant velocity of light. But you know, if it's getting faster as it's hitting, falling into the gravitational well, they would, claim or whatever, then that on its face is like a big wrench into the whole model. And then it gets into the Eddington experiment and the idea of, like they actually once tried to you look at this gravity, the way that gravity should interact with light, and they followed general relativistic predictions, and it ended up being way off. Like it was not within the relativistic predictions at all. But then of course they just turned around and claimed it as a victory for
Dude,
GR.
dude, not only that, real quick, not only was the prediction or the observation off, like it wasn't in relativistic favor. There was observations taken in tandem with that eclipse where two men were looking for gravitational redshift to correspond to the predictions of how much the frequency would change based off that. So based off of that displacement, Toby, they were saying that the frequency should change also, and there's a prediction that comes out of Einstein's equations to correspond to that frequency shift. And when what are they named? Charles St. John and John Evershade were doing their spectroheliograph readings during that eclipse. Guess guess what happened on whether or not they were able to detect gravitational redshift in correspondence with relativity theory.
0 detected.
0 detected. Not only that, they figured out that they could use transits of Venus and stuff to get redshift readings, and they never got anything to correspond with relativity theory.
Huh.
So
isn't that fun?
So even if even if there
big old Pound-Rebka problem.
Yeah, and even if there was a starlight displacement in this observation, you couldn't say that it was due to a gravity field because there's no frequency shift to back that up, back that interaction up. So that's unfortunate. Go ahead.
I'm sorry. Can you go back up to the slide with like the electromagnetic effect on like the shifting of the spectra? Because it looked pretty much like a redshift.
Spectra of the shifting. Where are we at?
Go up. Go way up.
We're almost at the beginning.
It was towards the beginning, but I don't know where you pulled the slide from. It was some dude's name with a Z in the 60s.
Oh, Zeeman.
Yeah,
right here. Right here.
Yeah, so you're saying electromagnetic effects cause redshift?
Yeah. So what happens is when an electromagnetic, or when they're analyzing the frequency of light, right, and it passes through an electromagnetic field or current, it what does it do? So like how they take readings and they get the emission lines and they're like, oh, this is due to hydrogen and helium because it absorbs at that rate or whatever. So what the Stark and Zeeman effect do is it basically doubles the lines of emission. So it kind of just like makes it doubles the lines essentially when it passes through the fields.
Okay. Can produce redshift via line splitting in the absorption lines.
Yep.
It literally says electrons move faster if they're going with the field.
Yeah, but I think, don't they say electrons are slower than C though? I think.
I guess, but I mean, like,
right up until you have to Thomas process them.
Right up until, dude, that's right. Right up until you have to Thomas process them, dude. I forgot about that.
Just every now and then, they may not be as fast as C, but every now and then they need a couple Lorentz boosts.
Dude, not every now and then, bro. Infinitesimally in perpetuity as they move in their orbit. So that's really cool. Yeah. All right. So
because I mean, if it's not if electrons don't move at the speed of C, then how does EMF work and how does radio work?
Oh, GG. You're right. So yeah, so the changing electron shell moves faster. So the reason for the changing electron shell, well, maybe they don't mean that it's moving faster than what it should be. Are you familiar with their electron shell model?
That's the old one, isn't it?
Yeah, but it's also whatever they need it to be. So I think like what they're saying here is like the jump from this ring to this ring or something, this interaction will basically cause that line splitting to appear. Because if when it's traveling with her against the magnetic field, it gets retarded or whatever, so it gets kicked down, or this will get kicked up, kind of thing. That's what I gather.
They don't even believe in this model anymore. They believe in like an amalgamation cloud or something weird. It's like a blob cloud.
Yeah, right. But they also believe in that when they need it, dude. So anyway, that's just what the interpretation of it was while this was coming out. Anyway, so doesn't matter. Stark and Zeeman were in like the early 1900s. these effects were
GG.
figured out.
Proving
So,
themselves. GG.
all right. So, where were we at, Toby?
I think we pretty much hit everything we wanted to hit today.
Man, all under an hour, dude. Not bad. Not bad,
Well, it's only been an hour?
dude. Right?
Wow. I was thinking it was 2 hours. Jeez. Well, yeah. I guess real quick I'll talk about that that thing I ran into in that Feynman lecture earlier last week.
Nice.
So I'll just read it. He says so he's talking about the electric current in the atmosphere. And he's saying that essentially if we measure the current over the sea, there's a daily variation, and the current varies by about plus or minus 15%. But here's the really interesting part. It's largest at 7 p.m. in London. The strange part of the thing is that no matter where you measure the current, in the Atlantic Ocean, the Pacific Ocean, or the Arctic Ocean, it is at its peak value when the clocks in London say 7 p.m. All over the world, the current is at its maximum at 7 p.m. London time, and it is at a minimum at 4 a.m. London time. In other words, it depends on the absolute time on Earth, not upon the local time at the place of observation. And so, yeah, the voltage at the top surface is dropping and rising by 15% with the absolute time on Earth. I thought that was just insanely fascinating.
Could we use Stellarium to see what the sky looks like at 7 p.m. London time on the equinoxes and the solstices? Because, I mean, I wonder if there's like some astral thing going on. Like, if it's like something like Orion's belt or just, it's got to be something.
Well, I think, like, I don't know if it would matter where it is, right? Like, it's the whole point is it's just a relative time to use. To say when, but it's like a global or worldwide phenomena. That the electrical field is rising and lowering all at the same rate. But yeah, it'd be the highest at 7 p.m. in London, but that would also still be the highest at like, what time would it be? Like in America, it'd be like 3 p.m. or like what 1 p.m. something like that.
Hey, Toby, can you link that paper, or is that from the Feynman lecture?
Yeah, it's from the Feynman lecture. I mean, I can drop my my highlights if you want.
Yeah,
Do they measure this all
my buddy wants
throughout
the
the year?
link to it.
What's that, Jesus?
Do you know if they measured this continually throughout an entire year or not?
No, actually, I don't. I need to look up what his sources were on this. I kind of just assumed it's not going to be nonsense since it's coming from the Feynman lecture.
I'm just thinking, like, the Elias effect seems to be based off a conjunction of celestial bodies. So if this effect is not consistent throughout the entire year, it could have been that during the time that he was measuring at 7 o'clock London time, there was a conjunction between the sun and some astral body, right? And then maybe throughout the year that time shifts.
Definitely possible. Yeah, I'd be curious to know what the measurements are based on. Yeah. Where's this paper? There it is. So yeah, I just dropped it in chat. Pardon my my excessive highlighting.
It's the best. That's the best kind of highlighting.
It's just like it's like about 70% of the lecture is highlighted.
Well, bro, you could make an entire presentation or multiple presentations just off of the stuff from like Galiev and Atsakovsky, bro. And that
Oh,
stuff's like,
absolutely. Well, even this whole electrical atmosphere, electrical ground, this whole thing is its own rabbit hole. And actually, I found a YouTube channel that I definitely would recommend for anyone that's interested in some ether engineering. My guy Evo, is it Master Evo, I believe? Yeah. This guy's channel is pretty interesting. It was crazy. I was looking for Steinmetz stuff, and I found some old Steinmetz readings. This guy was just reading straight from the book. And I was like, oh, this is cool. I like the way this guy's just reading straight from the book. I'm like, I wonder what he's up to now. And then I go to his channel, and he's doing this open source ether engineering. And his most recent video is about pumping electricity from the ground. Essentially, he uses resonance from two different coils in that are out of phase with each other but placed near each other, and it creates a dielectric field between the two of them. And then as that dielectric field builds up, it creates impulse currents. And when it crosses the dielectric field into the other side of the coil or the other coil, it creates like a negative charge or a positive relative to the ground. It creates a charge that sucks. It induces a current from the ground wire. Essentially, he induces a current from the ground wire. So he literally starts like pulling an electric current from the earth by using these resonant coils in this impulse pattern. Super interesting.
Can you link that channel, please?
Yeah, I just dropped his channel in the live chat and his that video of that specific most recent test that he did. And it's cool. At the end of every one of his videos, he's like, "This is all open source. I'm using Tesla's work, and I'm basically just trying to like further Tesla's work, and I'm keeping I'm sharing everything as I go. That way, no one can patent it or anything."
Dude, that's awesome that you found that guy. You're like, I wonder what this guy's up to. He was reading some Steinmetz a little bit ago. Now he's like, I made an electric resonance garden.
Yeah.
Dude, that's hilarious.
I've been like binging a bunch of his stuff, and even just the way he talks about his tests and stuff, it's been really enlightening. I like the way he talks about electromagnetism and dielectricity and stuff.
Dielectric and
That is
magnetic
super
induction.
interesting.
Is this the playlist right here? Generation.
That's specifically the most recent video, but he's got a bunch of content about it. About
Cool.
these like
Again, what year was this book written?
so he was reading from Steinmetz. Actually, I just posted that exact book. Oh, I thought I posted it in here, but maybe not.
Because I was looking, I think it was Galiev has like a 300, or maybe it's Atsakovsky, one of the two has like a 300 something page physics book, and it's like a full book of like physics, like all physics pretty much. Is
Yeah.
that the similar thing that Steinmetz made?
No. Well, he made one for electricity.
Here, yeah, it's in the docs tab here. But yeah, that's like pretty much everything I have for this week. Is there anything else we want to cover before we end the stream? We could end the stream early if it might not be the worst idea.
Yeah, I think that's ended on a quick note. Nice, clean 1 hour.
Yeah, I thought it was pretty interesting stuff. Cool. Anyone else? Any final words? Any comments before we close the stream out? All right, I'm gonna end my stream.
All right.
Thank you everyone for listening in. We'll be back possibly on Thursday evening. Are we gonna do that?
I don't know. I still got a lot of GPS ground to cover. Like,
yeah, let's just stick to the schedule. Next Tuesday, 7 p.m. Same time, same place.
Yep.
Or, dude, Toby, you totally gotta. I've barely been able to touch it because I'm on vacation, but you totally gotta check out the like the past decade, I guess. They've done a ton of